At Halmstad University, one of the main research directions is predictive maintenance with machine learning. CAISR is about building a world-class research center on machine learning using real data. And by doing this, we can be a partner for strengthening Swedish industry and making our education even better. And that's important. That's the role of a university. Predictive maintenance for us is about using usage data to better predict when equipment needs to be replaced or being serviced. Here, Volvo is an excellent partner for us.
Volvo Group is a global company with customers in 190 countries. Reliability of our products is very important for profitability of our customers, as it can increase the uptime and availability of the products for them. If the customer's wheels are not turning, they're making no profit. In order to increase uptime, we have predictive maintenance. Our predictive models have an accuracy of 3 months. Our Volvo Care customers are scheduled to visit workshops once in 3 months, so we can make sure that they have parts ready when they visit the workshops. For achieving the best predictive maintenance models, we need the state-of-the-art, and that's why we work with external partners like Halmstad University.
The CAISR turbocharger predictive maintenance project was born out of a long dialogue together with Volvo on important pieces of equipment that we need to have predictive maintenance for. So the turbocharger is a very expensive piece of equipment, which means that you put a lot of engineering effort into building it. It shouldn't break, but still you want to be able to predict if it's going to break because it's that important.
Based on the prediction of the model, dealers, customers, and all end users know which parts needs the maintenance. Turbocharger is one of the most vital components. Therefore, having a robust predictive maintenance solution is essential. At the moment, we can predict 80% of the failures on the vehicles. However, we are striving to increase this number to 100%. That's where Halmstad University comes in. They can help us increase the performance and robustness of the model.
When you have a well-engineered component like Volvo's turbochargers, the failures become a rare event. And that makes the prediction of failures really hard, because most of the data we have is coming from the healthy situation. The method we tried in this project was using survival analysis, which means that the devices have never failed. And still the model is able to consider information from these devices, because we know that they haven't failed up until the time of observation. By considering this method, we can actually improve performance compared to the traditional remaining useful life prediction methods.
Even two similar trucks with the same operation, operating in two countries with different topologies and weather conditions, would behave differently. This leads to considerable sensor measurements variation between different conditions, which in machine learning terminology we call it a domain shift. Most traditional machine learning methods ignore the domain shift problem. This leads to missed failure prediction, false alarms, more maintenance cost, and also more downtime. The first thing that we needed to do is to detect if there is domain shift or not. Once we detected the shift, we used a specific type of neural network called Domain Adversarial Neural Network, for short DAN. DAN basically consists of two branches. One branch is responsible for solving the task, in our case, remaining useful life. The other branch is responsible for aligning two different domains, in our case, two different operating conditions.
After applying DAN, which is represented on the right plot, you can see there are much more alignment, which leads to better generalization of one domain from another domain.
Sometimes we have a scarcity of data in one country, while we have abundance of data in another country. In those circumstances, a method like DAN could come handy, and we could use it to transfer the knowledge from one domain to another domain in a much better way. When we use DAN, we gained a considerable improvement in performance of our remaining useful life prediction.
I'm really impressed with the results that this group has achieved. The turbocharger project was a real challenge in the terms that there were so few pieces of equipment that actually broke, and you could still make a prediction that is like 90 days in advance. That's so much better than what it looked like from the start that I'm so happy about these results, and that the machine learning could show that they could do that.
Predictive maintenance is an exciting field and will change the way we do transportation for the future.
The future is intelligent, and I envision a future where things will not break. The predictive maintenance will be so good that you actually replace them in good time before they actually break. And Halmstad University will be contributing very much to the machine learning side of doing predictive maintenance algorithms.